Hi, everybody. This is the second part of our lecture on work and energy. Today, we're going to focus on, first, we're going to review how we do these problems with a pretty good example using a spring. Um, and then, and we'll talk about the algorithm that I want you to use to solve energy problems. Then we're going to talk a little bit about friction, well, a lot about friction actually, and how you handle friction, including two examples, and one of them is super important. So the second friction example, really important that you understand it. There's a weird little wrinkle with friction about where we put the work due to friction and how we handle it in energy after friction happens. We'll talk about that. Then we're going to talk a little bit about potential energy diagrams, which are particularly useful in biology and chemistry and engineering and physics, of course. You should know how to identify them and what they're telling you. You may have a homework question on it, which will be just kind of an analysis of a PE graph. And that can be a little difficult, but if you understand what you're looking at, it's not too bad. And then we'll talk a little bit about power. And you may think you know what power is, but we're going to put it in a mathematical description and talk about what power actually means in a couple different cases. And then finally, we're going to do a putting it all together problem. And that problem, I'm going to talk about how you solve it. I'm not going to go through and get to numbers because frankly, that would just take forever. But at this point, or at that point, when we get to the end of this lecture, you should be able to put the numbers in whenever you want, if you want, and try and solve it. Okay, so let's start off by reviewing our algorithm. And our algorithm, if we have a problem, so let's say we have a free fall problem. So we have a particle that we're going to drop some distance, or we have a particle that's moving to the right and it goes up to the top of a hill. And we want to know how fast it's going once it gets up there, or friction region or whatever. The first thing we do is we choose a couple of positions that are relevant to us. And by relevant, I mean, if I'm asking you for the final velocity, right, then the initial and the final position, the initial position where it began the motion, the final position are relevant. If it's like how fast is it going to go when it gets to the top of a hill or the bottom of a hill or whatever. So you choose the positions that you care about, that you're seeking to find out something about the motion at that position. And then we make sure and we label anything relevant. So if we're dropping this from rest, obviously we say that V initial or VA here is 0. And if I told you this was 10 meters high, we can choose that Y at A is 10 and Y at B is 0. Same if I told you this was 10 meters high, Y at A is 0 and Y at B is 10, right? We need to know why, because the Y tells us how the potential energy of gravity is going to change. We may need to know the X position for a spring or for friction. We'll find that out later. If you know K and you know M, if they're given, write them down. If they're not given, you may have to solve for them. And that can be a little bit of a challenge. In order to solve for M, you have a little bit of a problem if it's not a spring, because all the terms have M and M canceled. So in general, you'll be given M. You'll in general be given K. You may have to solve for it, but whatever. And then what we do is for every position, so in this free fall one, at A, we write that the energy of A is equal to mgya, or ha, whichever way you want to see it, kxa squared over 2, and mva squared over 2. Similarly, we write this for B. So for every point, you write what the energy is going to be. And just do this without thinking about it. Just get in the habit of not being lazy and just write them down. And eventually you're going to get to the point where you know that, like, initially this has no velocity, so we don't need to write it. And this has no spring at all in this problem, first problem. Second problem doesn't have a spring either. So you could ignore those terms. But for now, especially if you don't know what you're doing yet, all you have to do is write all three types of energy, period. And then cross out the ones that you know are either zero or are terms that don't matter, like the spring terms, because there's no spring here, right? Once you've done this, you set the energies equal. Assuming there's no external force, meaning friction, we can do this. And so what we get is that mgya, we also, I'm sorry, this should have been a b. We know here that in this free fall one, this was 0. So we get that mgya is mvb squared over 2. And from there, we could solve for the final velocity because we know ya was 10. And we know the mass, let's say, was, I don't know, 5 kilograms. Okay. The other thing that I mentioned in last lecture is if you want to use g is 10 meters per second squared, I'm okay with that. That's totally fine with me, unless I tell you to use 9.81. I'm going to tell you that if something is close, right? Perhaps we're trying to figure out the exact distance or the exact, like trying to go off a cliff. If there's friction, is the friction enough to stop it from going off the cliff? You may want to use 9.81 and not round it up, because you'll get a different answer in that case. And you may get an answer that's that, you know, says, oh, the car didn't slide off the cliff because of friction, but it turns out that if you use 9.81, it did. So in general, you can use 10 if you're just trying to kind of ballpark numbers, and I'm totally fine with that. If I want a specific analysis of a problem done, I'm going to ask you on an exam or a quiz, let gravity equal 9.81 meters per second squared, okay? So the reason why we do that is this becomes super easy if we use 10 as g, right? Because this is 5 times 10 times 10, this is 500. And this is 5 over 2, which is 2.5, right? So 500 divided by 2.5 is what? 200? So 200 is equal to VB squared, and you can just plug in square root of 200 into your calculator and get VB without having to do, without having to enter numbers into your calculator. Because trust me, your calculator is a time sink. What that means is you waste time with your calculator. If you can get away from using your calculator as much as possible, try and do it. Try and do your basic arithmetic and algebra. Do it before you touch your calculator, and use your calculator the least amount as possible, right? I don't know what the square root of 200 is. I'll use my calculator for that. But finding that VB squared is 200, I can do that in my head, or I can do that on paper pretty fast, right? Because really, here, right, the 2 comes over and the m, and if you divide these go away. These cancel, and you get 2 times 10 times 10 is 200. I can do that in my head and then just take the square root of 200. I don't need to put 2 times 9.81 times 10 into my calculator. Just round it up to 10. You can do that in your head, right? Okay. So I've gone through this, and I kind of talked about it for this free fall one. And you could figure out how to do it for the one going up the hill. We are going to do it for a problem with a spring, because springs are a little bit tricky because you have equilibrium of the spring. So in this problem, and I should note, I stole all the graphics that I didn't draw straight off the internet. Sorry, I really should have noted where they came from, but this is for our class. Just keep in mind that these all came from the internet. They are not my images. I did not create these images, except for the ones that I hand draw. Anyway, So in this problem, we have a horizontal spring, okay? And we're going to start by placing a mass on this spring, compressing it some distance, they're calling it D, and then releasing it, and we want to know how high up it goes, okay? So once released, what is the velocity of the ball as it loses contact with the spring? And we'll talk about what that means, and then what max height. So we really have two different problems to talk through here. But fortunately, we can write the energy at A, B, and C, and from those, we can figure out the two things that we were asked for. We're told the mass of the ball is 0.2 kilograms, 200 grams, that it's initially at rest with the spring compressed, right? So we'll talk about what that means in a minute. We're given the spring constant K is 450 newtons per meter. Spring constants are always newtons per meter. The reason being that force is Kx with a negative sign, and therefore K is F over X, right? With a negative, but whatever. The units are going to be newtons per meter. And we're told how much the spring is compressed by. So if we go back to our algorithm and we look at our algorithm, the first thing we need to choose is the relevant positions. Now, I'm going to say that my first relevant position is A, and that is when the spring is compressed and it's not moving. So the initial part of the problem. My second is B, and this is also B. And that's right when the ball is clearing, right? It's heading upward, but it's just clearing the spring. Once the spring, if the ball or particle isn't attached to the spring, I talked about this last time, once it clears equilibrium, the rest length of the spring, which is what this is, it is no longer in contact with the spring. And you can ignore the spring as it heads up after this point. We know that the way this is drawn, we really shouldn't have V here. We know that V at the top is 0 when it reaches max height. So we want, when it gets to H, we're going to call that our C position. Those are the only three positions we care about. We care about the initial position when it's compressed. We care about the velocity right when it clears the spring. So we care about when the spring is at equilibrium and the particle is leaving the spring. And then we care about max height. So we have our EA, our EB, and our EC. We need to figure out the relevant variables here, and we'll talk about those. But we have a spring, so we're going to have Y, and we're going to have X for each one. We're always going to have a V for each one. And that's all we need, okay? So at A, at B, and at C, let's talk about what these are. Where do we want to put Y is equal to 0? What I'm going to do is I'm actually going to call, when this thing's at equilibrium, I'm going to say this is where my Y is equal to 0. I can choose Y to be 0 wherever I want, as long as I'm consistently measuring for B and C from, or A, B, and C from that 0 point. So when it's at B, I'm going to say Y is 0. Hopefully that makes sense to you. So when it's at A, I need the compressed distance. And it was compressed 2.8 centimeters. So this distance is negative 0.028 meters, 2.8 centimeters. It's negative because we defined 0 to be at B, and we were initially compressing it. So negative 0.028 meters. I'll do this just so that we don't have things. Now C, I don't know, but C is going to be H, right? It's going to be my maximum height. I don't know what it is, but I know it's a positive value of Y and it's H. The V is easy because V of A is 0. It's initially compressed, but it's not moving. We haven't released it. And V of C, we know from projectile motion and free fall motion that when the motion starts heading upward against gravity initially, at its highest point, the velocity in the Y direction is 0. We don't know what V is for the B. We don't know what V is right when it clears. We were asked to find that. All right, so now we need x. And this x isn't the right to left or left to right displacement, it's the spring. So the reason why we also chose y to be 0, we're going to choose x to be 0. We're not going to actually choose that. X is 0. It has to be 0 where the spring is in equilibrium. Okay, that occurs when it's at B. It's initially compressed 0.028, and here, Na. Once it passes 0, because the particle is not attached, we don't care about the spring. It's like the spring isn't there anymore. If the particle was still attached, this thing could go up and down, like a bungee jumper in reverse, right? Instead of bouncing up and down under a bridge when you're tied to a stretchable rope, it will go up and back down, up and back down, up and back down. With gravity being the only thing that's gravity pulling it down and the spring pushing it back up and blah, blah, blah. Okay, so we have our variables. That was the second part of our algorithm. This was the hard part though, because once we've done this, once we've figured out what our variables are at the different positions, the only thing left is writing our energies. And those, we can turn our brain off, right? For EA and EB and EC, we write all three types of energy. MGYA plus MVA squared over 2 plus KXA squared over 2. And before I write all these, I'm going to write here. I'm going to go to here and do it because I put these slides here for a reason. So EA, EB, and EC. All right. So we know this is MGYA. This is KXA squared over 2. This is MVA squared over 2. MGYB, MGYC, plus KXB squared over 2, KXC squared over 2, MVB squared over 2, MVC squared over 2. You should be able to write this without anything. All you have to know is the three types of energy and that you can write it for each one. So on an exam, you better be able to get to this point. Maybe your variables are messed up, but you better be able to get to this point. Now though, if we go back and look at our variables, for A, V was 0. It was initially at rest. And for C, VC was 0. If we look here. We also know that when it reaches equilibrium point, when it's at position B, Y and X were 0. So these guys go away. And finally, we said that once it cleared the spring didn't matter anymore. Okay, so all we're left with is this term, this term, this term, and this term. So the next part of our algorithm is that we set EA equal to EB equal to EC. That's conservation of energy. There's no external non-conservative forces happening here. The only forces are gravity and springs, or restorative forces. Therefore, the energy is always conserved. We assume. So no air resistance, no friction, no nothing. That being the case, we can then write this as MGYA, right, is equal to, I'm sorry, there's a KX here too. KXA squared over 2 is equal to MVB squared over 2 is equal to MGYC squared. We were told that M was 0.2 and K was 450. So if M is 0.2 kilograms, K is 450 newtons per meter. And then we know that YA, YB, we don't need YB, sorry. We know that YA and XA were both minus 0.028 meters. And we know that We don't know YC, but YC is H. We don't know VB, but we want it. So we want these two things. And so what we can do is we can do this in a number of ways. We know everything here. We know everything here. We don't know VB and we don't know YC. So you could either set up an equation that looks like this. Plus kxa squared over 2 is equal to mvb squared over 2 and then solve it for VB. Or you could do this. mgya plus kxa squared over 2 is equal to 0.2. Again, g is 10. And ya was minus 0.028 plus 450 divided by 2 times 0.028 with a negative sign squared. And this is 0.2 times 10 times 0.028 with a negative sign. So this is negative 0.56, right? And then plus 450 divided by 2 is 225 times 0.028 times 0.028. And yeah, they're negative, but the negative signs cancel. This is this is 0.056. And this is plus 0.1764. Okay. These are joules. Both of them are joules. This ends up being 0.1204 joules. That is the energy at any time. So what you could actually do is say that mvb squared over 2 is equal to 0.1204 joules, and mgyc is equal to 0.1204 joules, right? So you could solve them algebraically, or you could just find the energy, and you know that the energy at every point is equal. So doing this, I get VB is the square root of 2 times that divided by 0.02 or 0.2, and taking the square root, and I get 1.1, basically. 1.1 meters per second. And then I can solve for this for YC, which is really H. So YC is equal to my H by taking 0.1204 and divided by mg. So 0.1204 divided by 0.2 times 10, which is 2. So this is 0.06, 0.0602 meters, 6 centimeters. Okay, that's it. I know it's a lot. I know I went fast through it, but that's your algorithm. You figure out where the positions you care about are. You figure out what your variables are. You write down the energy. Just the only 3 terms we have are these 3. When we have friction, we're going to add something, but you just write down those 3 terms. Then you start plugging, you set the energies equal, assuming that everything's conserved. The only time it won't be conserved for us is if we have friction, but we'll talk about that later. So you set all these energies equal, and you go back and you look at the terms that survived and you set them equal to each other. And from there, you solve for what you want. It's pretty simple. It's actually harder to describe than to do. It's actually pretty fast to just do it. But once you get this kind of down, you could even do these steps in reverse. Write this down first once you've chosen these, and then figure out what your variables are. That's fine too. I don't really care. But as I said, the hard part is really right here. This is the part where you have to be on your toes and make sure that you understand what your variables are and what's going on with the spring, where you're choosing your 0 to be for your Y. Your 0 for your X is always at the equilibrium. The spring can be vertical or horizontal. The other thing that we're not going to get into too much, but it could also be in two different directions. Think about projectile motion. We could use energy to solve projectile motion and figure out what the energy is in the X when it starts and ends. Well, the energy in the X is just the kinetic energy, right? There's no acceleration. There's no force doing any work. Gravity is not doing any work. There's no springs. So in the X direction, you only have kinetic energy, right? And it's always the same kinetic energy. In the Y, the kinetic energy in the Y, and then at the top, it's all potential energy in the Y, and then back at the bottom, it's kinetic energy in Y. So here it has kinetic energy in the X plus kinetic energy in the Y. This is projectile motion. Here it has kinetic energy in the X plus mgy, because all the kinetic energy in the Y turned into potential energy of gravity. And here it has kinetic energy in the X plus kinetic energy in the Y again. You could do projectile motion as an energy problem. You just need to remember that you have to divide them into separate directions and then add the energies together to figure out what the energy is at the end. But the energy is conserved in X and the energy is conserved in Y. It's conserved in both. It's actually pretty fun to do. It's not super difficult, so I'm not going to do it, but try it for yourself sometime. Try to do projectile motion with energy and not the constant gravity equations that we learned. It's kind of helpful. You'll understand what you're doing if you get the answer right, I guess. So, okay. So we talked a bunch about gravity and springs or restoring forces, that these forces are conservative, that energy is conserved. And what a conservative force means, well, first of all, we say that if there's no external force, there's no forces but gravity and restoring forces acting on the system, then the mechanical energy is conserved. And that's because the mechanical energy, which let's write it ME, is the potential energy plus the kinetic energy, okay? And that's always a constant value. So if the kinetic energy changes, the potential energy changes. You lose some kinetic energy, it becomes potential energy. You lose some potential energy, it becomes kinetic energy. That's how gravity and restoring forces work. Essentially, gravity can store energy, and springs can store energy as potential energy. And any kinetic energy that's lost becomes stored in potential energy, which can be released later in the motion of the particle. That's what a conservative force is. There's a couple of things a couple of other characteristics of conservative forces, which are really nice. But essentially, the idea that the mechanical energy is always a constant value means you could set it to be zero, right? The mechanical energy is zero, which is fine. That doesn't mean the potential energy and the kinetic energy is zero. That means that when you add them together, you always get zero. Or you could set the mechanical energy to be 1 billion joules. That's fine too. As long as it's a constant value, what's going to happen is whenever PE decreases, kinetic energy increases. Also remember that PE is your gravity potential and your spring potential. And KE is your kinetic energy. And those two things, basically, potential energy and kinetic energy can exchange themselves, right? And they could be exchanged between the potential energy could be exchanged in some weird problem. You could probably come up with a way where you exchange potential energies, and that's fine. But mathematically, what a conservative force means is that if we take an integral over a closed path, no matter what path we take, we always end up with zero, okay? this might bug you a little bit because what we're saying, you've learned area under the curve and stuff, right? And what we're saying is that no matter what path we take, right? If we go under or over, it doesn't matter. Excuse me, I'm sorry. What we're saying here is that conservative forces are path independent along a closed path. They always end up being zero. What that means is that we only care about the endpoints. We only care about the position at A and the position at B, and we figure out the potential from there, or we figure out the kinetic energy from at those endpoints. And we don't care how we got there. Another way to think about this is you hold a ball in your hand, right? Let's say you're holding it a third of a meter above your desk. You then get up and hold it over your head and walk into your kitchen and walk around your house and move it down to the floor, and you come back and you sit down and you hold it again a third of a meter above your desk. No matter how you moved, it began with a potential energy, mg times a third of a meter above your desk, and it ended up there. And it doesn't matter if you moved it to the right and then back, or if you moved it up and down and came back. The only thing that matters are your endpoints. There's a little subtlety that I'll get into on the next slide, but we really don't care. We only have to concern ourselves with endpoints, with the positions on the path, not how it got there. So we could even say, well, imagine that this was position C, and imagine somehow this blue goes through and this green went through, right? It doesn't matter how we got to C, which of those paths we chose, the change of kinetic energy and potential energy when we go from A to B, there can't be, they have to equal sum to zero, right? The energy at A and the energy at B and the energy at C and the energy at D, always the same. So the energy is path independent. That's really, really, really helpful, because what that means is we don't have to do these crazy integrals anymore. We can write down the energy. The reason we can just write down our energy at different points is because we don't care how we got there. In a way to show you by counterexample what the difference is, right? So imagine you're sliding, right? Okay. Imagine you go this way and you're somehow able to turn and head back the other way, right? If you had, sorry, I don't want to do it that way. So I guess if there were friction in here is what I want to say. If there were friction, because friction depends on the displacement, friction depends on the path. Friction's a non-conservative force because it always depends on how long your path is. And so this is obviously, this green path here is obviously much longer than the red path. I would guess the blue path is even longer than the green. If each of these paths had the same coefficient of friction on them, right, the amount of work, negative work, the amount of energy taken out of the system by friction would be greatest for blue, a little bit less for green, and less still for red. So the energy when you got to B would be much less, right, if you took the blue path, if there was friction. And it would be a little bit less if you took the green path, and it would be the least amount of energy would be lost along the red path. However, if there were no friction, no non-conservative forces, the energy at A and the energy at B are always the same. Doesn't matter what path we take. I hope that makes sense to you, right? So when you have a non-conservative force, it's based on the path. That should totally make sense. Non-conservative forces are path dependent, and you'll end up with a different amount of lost or gained energy from a non-conservative force. The only non-conservative force we care about in this class is friction. And we're going to deal with that in a special way when we get there. One thing I should note, though, there's one caveat here, one exception here. And that's that, yes, it's path independent for gravity, but gravity, what we care about is we care about the change in height. We care about the work done by the force of gravity, which is down, right? These mg's are down. So the work is F dotted with delta H, right? So even though this path, what we care about is we care about the change of H. And if we took this path, right, both of these paths, the change of H is the same to go from A to B. So the potential energy change is the same going from A to B. It's still path independent, but what we care about is we care about the H. And why this comes up is, again, if you have a block on an incline and it's going to slide down 2 meters down the incline, and you're told what the angle is, the change of H of this block from here to here, this is 3 meters, right? This distance, though, is a triangle with a hypotenuse of 2 meters. I keep saying 3, but I wrote 2, so I'll write 2. And so you know that this H is the hypotenuse, 2, times sine of the angle. So that is your delta H in regards to the potential energy change of gravity. If you're on an incline, you need to figure out what H is, not what the distance down. Where things are going to get tricky is friction does depend on the change of X. So if you were sliding down an incline, friction would depend on X. The change in potential energy of gravity would depend on H. And that's because work is done in the direction of the displacement or in the direction opposite the displacement. It's a dot product, right? I hope that makes sense. It's one of those things where it makes a lot more sense once you do a couple of these examples with like an inclined plane, and we will. You'll see it right away, right? Okay, so moving on. Non-conservative forces. We haven't talked about non-conservative, we haven't talked about friction really yet, but non-conservative forces, like friction, if it's friction, the work done always results in a net loss to the total energy. So we're going to lose energy from friction. Can we make sense of that in what we already know? Well, we know that the work is equal to the change in kinetic energy. And the change in kinetic energy is mv final squared over 2 minus mv initial squared over 2. But if v final is less than v initial, if something's taking energy out, it slows it down. In order for this to be negative, this work to be negative, v initial has to be greater than v final. And the work done by friction is always negative because as the particle travels, delta x going right, the force of friction always opposes that displacement. So it's always in the opposite direction. So F dot delta x here would be negative force of friction, delta x cosine of 180. So we really don't need this. The cosine of 180 tells us that these two things are opposite. The picture also shows us that. So what this gives us is negative force of friction times delta x, right? And we know that that negative force causes an object to slow down. From our practical experience of being alive, we know that friction causes an object to slow down, okay? The force of friction always opposes the displacement of our particle. Whichever way the particle is traveling, the friction vector is in the opposite direction, assuming there's a surface with friction. The work done by friction is path dependent. right? What that means is you have to figure out how far it travels on the surface with friction in order to figure out how much work was done by friction. It'll be negative work. How much energy was lost to friction depends on the path you take. And that's pretty obvious, right? I think it's obvious. Imagine you're trying to get your car to stop, right? And you're stopping it in a straight line with friction, or you're weaving and you're trying to make it so that the path is as long as possible. The longer the path, the more friction is able to do work, the more negative work is done, the more energy is removed from the system. Friction is path dependent, okay? So let's talk about our definition of friction. We had from back in chapter 6 that friction was mu times n. And we need to remember that on a flat surface for an object, n is up and weight is mg. Therefore, n is mg on a flat surface on a inclined plane at some angle, right? Since mg is down, the weight down the plane is mg cos theta. I'm sorry, the normal force down the plane. If this is the normal, we break that into a y and an x, and we get mg cos. We did that a bunch in chapter 5 and chapter 6. I'm not going to go back through that. I just want to make sure you remember that when we're figuring out the friction, if it's on an inclined plane, you got to use the normal force of the plane, not the normal force that it would have for a flat object. Okay, so we know this force is negative mu n. The force dotted with dx is negative mu n dx, okay? This is super easy because these two things are constants, right? And so when you do this, you get negative mu n times the integral of dx from x initial to x final, and that gives us this, right? We're gonna almost every time assume that x initial is 0. In fact, I'm gonna just leave this off. And when I say x final, what I really mean is I mean the distance that it traveled. I'm calling delta x, x final, right? Sometimes we'll call this d for the distance it travels just because we're reserving x for our springs. So you might want to call it d. You might want to call h, y direction h. It's really up to you. Just make sure you're clear on, that the work done by friction depends on the force, mu n, and the displacement, d or x final or change of x or whatever you want, right? And it's always negative. It's always pulling energy out. But that leads to a very, very tricky problem, okay? So imagine we have friction, right? And so this thing begins with V at A. I'm going to call this position A, and it's sliding that way with VA. And there's a region of friction that's D long with a coefficient mu. And we want to know, once it gets to the end of that friction, and it stops, right? So VB is 0. We want to know how much work was done by friction. In fact, let's not call that 0. Let's actually say it passes through a region of friction, but it's still going at B with some velocity, right? I want to do that for a specific reason that I'll talk about in a minute. So we have the energy at A, right? And I'm going to leave off the spring. So we would have mgya. Actually, I'll put it here for a minute. Plus mva squared over 2. Ya and yb will be the same. We can forget about this term. There's no springs in this, so forget about this term. So at EA, we have mva squared over 2. And at EB, we have mvb squared over 2. However, we know the energy is less at B than it was at A because friction took energy out of the system. So we can do one of two things. We can either write that EA minus the work done by friction gives us EB. So whatever energy we started with minus the work done by friction gives us the energy at B. Or we can say that the initial energy is equal to the work done by friction, and it becomes positive, the work done by friction plus the energy at B. This, you wouldn't necessarily think it, but this causes a lot of confusion, a ton of confusion. Essentially, your total energy that you started with becomes your final energy plus the energy of friction, or the energy you started with minus the work you lost to friction becomes your final energy. That's important because in our algorithm, we're being taught to write down EA is this, and EB is this, right? And EC is this, and then setting them equal. But we need to figure out where to put the friction. We need to figure out what to do with friction. And we're going to have two examples. The second example is really, really, really important. But we know the work of friction, right, is negative mu n, and you need to figure out here it would be mg. If this thing was sliding down and inclined, it would be mg cos times d. However, this negative sign is only there. This negative sign isn't important. So we really should write this. I mean, it's important, but we really should write this as the magnitude of the work of friction is mu n d. It's negative if we put it on the side of the equation with the initial energy. It's positive if we put it on the side with the final energy. You'll see that in action. It's, just trust me, and I'll try to point it out. But what I want to get clear to you is this sometimes bothers people. Their intuition says that this is wrong, and they want to put a negative sign in here. That the final energy minus the work of friction gives them the total initial energy. But that makes no sense. If I went to the store with $20 and I spent $10 and I had $10 when I came home, right? My initial energy would be 20. That would be the money I have left plus the money I spent. Or my initial money minus the money I spent gives me the money in my pocket. Make sure you're clear on that, right? So the work done by friction is positive if you add it to the final energy. That gives you the total energy. It's going to bite you at some point. Do not write the work done by friction as negative mu nd. Write it as mu nd, and either it goes here with a negative sign or it goes here with a positive sign, okay? We'll talk about that. All right, so what we're gonna do in this problem, which is actually pretty easy, this is a pretty easy problem. We have a block that's sliding initially before it hits friction with V of 2 meters per second, and it's headed to the right, and the mass is 5 kilograms. It then goes through this region of friction where mu is 0.22. And it slides until it stops, okay? So we don't know what D is. We're gonna figure out what D is here, but it slides until it stops. And we wanna know how far it slides. So we're gonna choose A to be our energy before it hits friction and B to be our energy once it stops. The only variables we care about here is we're gonna need to write mu mg because n is mg if it's on a level surface, times d, that'll be our work of friction. We won't have mgy. Mgy A is equal to mgy B. We'll choose y to be 0 along the surface, and therefore these are both 0. There's no springs, so no kx squared over 2's. So the only thing we have is we have the energy at A is mva squared over 2, and the energy at B is mvb squared over 2. And then we can do one of two things here. And we're also going to note that VB is 0. So this is 0. So we can do one of two things. We could either say EA plus the work of friction, I'm sorry, not plus, the initial energy minus the work of friction is EB, or the initial energy is the energy at B plus the work of friction. Whichever way you want to see this. We know that this is 0. So we're going to say this is 0 and this is 0. We know that the work of friction is mu mgd, right? So here we get mva squared over 2 minus mu mgd is equal to 0, or here we get mva squared over 2 is equal to mu mgd, no negative sign. The m's will cancel. We can see that if we write mva squared over 2, remember va was 2, right? 2 and 5. M was 5 kilograms, is equal to mu mgd, where mu was 0.22. We don't need the m's, they cancel. Va is the square root of 2 mu gd, right? And so this would be 2 times 0.22, which is 0.44, times 10 is 4.4. Oh, nope, I'm sorry. I don't want to do that. I'm solving this for D, aren't I? So D is VA squared over 2 mu G. So this is 2 squared over 2 times 0.22 times 10. So this is 4 divided by 2, which is 2 divided by 2.2. And so D is 2 divided by 2.2, and 2 divided by 2.2 is 0.9 meters. 90 centimeters. It's actually 91 if you want to round. Okay, 91 meters is how far this thing slides before it stops. What is the force of friction? Well, the force of friction was mu mg, and that was 0.22 with a negative sign, times 5 times 10. That's 50 times 0.22. 0.22 times 50 is 11. This is negative 11 newtons, right? That's the force of friction. The work done by friction is the force of friction dotted with D. They are in opposites, so this is negative force of friction times D, and D was 0.91. So 11 times 0.91 is negative 10.01 joules of energy, or 10.01 joules of energy were lost to friction. What was our initial kinetic energy? You don't have to compute it, we can. It was mva squared over 2. This was 5 over 2 times 2 squared. This is 4 times 5 is 20 divided by 2. This is 10 joules, right? So we can see that our answers don't quite match, right? They're a little bit off from rounding, but basically we initially were traveling to the right with 10 joules of energy. It was all kinetic energy. We slid through this region of friction and came to a stop. So we know that the amount of friction, the amount of work done by friction, was negative 10 joules of energy because it came to a stop. When it stops, its kinetic energy is 0. It lost all of its kinetic energy to friction. The big key here, though, is actually this part right here, that we either subtract the work done by friction from the initial energy, or we add it to the final energy in order to get the equation right, okay? Things are gonna get a little bit more difficult in the next example. And this is something called a roller coaster problem, because roller coasters at theme parks go up and they go down and they do loops. We're gonna see a real roller coaster problem at the very end. But for this one, what we want is this block is initially sliding on a frictionless surface Comes to a hill, it goes up the hill, and then it has a 3-meter long surface with frictional coefficient 0.25, and then it slides down to another region with no friction. And we want to know what V final is here, and we want to know what V is when it initially gets to the top, and we want to know what V is before it begins to go downhill, and we want to know blah, 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 blah. Okay, so notice also that this first hill is 1 meter above the surface, and the second hill drops 2 meters. So our first thing that we need to do is choose the areas that we care about. I'm going to say A and B. I want to know the energy here and the energy right before it goes up the hill, once it reaches the top of the hill, once it reaches the end of the friction, but before it starts heading down the hill, once it gets to the bottom of the hill, and at the end. Okay, so our next step is, what are our variables? Really, where is y equal to 0? I'm going to assume it's initially equal to 0. So this is where my y is 0. And if that's the case, then here at yc and at yd, y is equal to 1 meter. And at ye and yf, y is going to be negative 1 meter, because it was at 1 meter, 0, negative 1, right? It's a drop of 2 meters. And at ya and yb, y is equal to 0. Does that make sense, I hope? So we start at 0, we go up 1 meter, we go down 2 meters. Okay, so let's do this. A, B, C, D, E, and F, and we're gonna write Y, and we're gonna write V, and then we're gonna actually write D for where there's friction. There's no springs in this problem, so we don't need to worry about X at all, although this is, you could call this D or you could call it delta X or whatever. So at A, this is going to be 0 for everything except between C and D, this is 3 meters. Just otherwise, I don't care. Yeah, I really shouldn't write this down. I should really only write I and B. But what is Y at A? 0. What is Y at B? 0. They're both along where we chose 0 to be. At C and D, it's 1 meter and 1 meter. At E and F, it's from D to E, it dropped 2 meters, so this is negative 1 meter and negative 1 meter. V at A was 10 meters per second. Do I know V at B? Yeah, if there's no change in gravity and no spring, then this is still 10 meters per second. And it turns out that the energy at A and the energy at B are identical because nothing happened, nothing changed. No friction, no change in potential energy due to gravity or due to a spring. I don't know what it is at C. I don't know what it is at D. I don't know what it is at E. And F is going to be whatever V E is. Again, from E to F, there's no change in the energy. There's no potential energy change. There's no potential energy change of gravity or potential energy change of the spring. There's no friction there. So essentially, I really don't need A and B. B and F. I'm gonna leave them on there, but I'm just gonna write that EA is equal to EB and EE is equal to EF. And we'll just use EE and EA. All right, so what is our next step? And that's the easy step, right? We write EA, we write EB. I'm gonna stop at ED for a very important reason. Here we write MGYA, MVA squared. I'm gonna leave springs off, although I would expect you to write them if I wanted you to do this on an exam, because again, I want to see kind of your process, and your process should be to remember to write down all types of energy available and then cross out the ones that don't matter. So if you don't want to write them, at least write no spring So no kx squared over 2 terms. And that's fine. Okay. But we have friction. We have friction between C and D. So this means that EA is equal to EB, and there's nothing but gravity and spring forces here and kinetic energy. So the mechanical energy between EA and, or A, B, and C is all conserved, right? But between C and D, we lose energy to friction, right? So there's some work done by friction between C and D. And therefore, we have EC and ED. And again, you can either add the work of friction to ED or subtract it from EC. I'm going to actually subtract it because I want ED later on. So ED, we need to remember that ED is EC minus the work of friction, and that the work of friction, in this case, the normal force is up, so normal force is mg, so this is mu n times d, which is mu mgd, and if you prefer, write it like that. The negative sign is taken care of here. Then, right, if we do that correctly, then EE is equal to EF, and they're both equal to ED here, if ED is EC minus work of friction, right? If you tried to do this, you would get EC, right? But EE and EF aren't equal to EC, they're equal to the energy after. So we're gonna do something a little weird. We're gonna write the energy at A, B, C, D, E, and F, and we'll see. This is what the energy is. We're gonna write what V is, we're gonna write what Y is, and we're gonna write mgy plus mv squared over 2 for these, sorry. But I want you to see what the energy is, okay? So the energy at A, right, there's Y is 0, and at B, YB is 0. So this is mv A squared over 2, and this is mv B squared over 2, but they're equal. So VA is equal to VB, and VA was equal to, what did we say? 10 meters per second. And VA is 10 meters per second. So the energy here, this mass is 3 kilograms. The energy here, there's no Y, Y is 0. So this is 3 divided by 2, which is 1.5, times 10 times 10, which is 100. So 1.5 times 100 is 150 joules. It still has 150 joules here. 10 meters per second, 10 meters per second. That's because the kinetic energy is the only energy it has. Its Y value hasn't changed, so gravity's done no work. There's no spring, so no spring has done any work, and there's no friction to be lost. Here, however, remember that mgyc plus mvc squared over 2 is now equal to the energy at A or the energy at B. We know that our YC, if we look here, was 1 meter. So this is 1 meter. Therefore, 3 times 10 times 1, this is 30 joules. And we need to figure out what VC is. And this, right, we already said was 150 joules. So this term has to equal, so MVC squared over 2 is equal to 150 minus 30, which is 120 joules. If I multiply that by 2, that's 240, divide it by 3, that's 80. So I get that VC is the square root of 80, which is 8.944. So this is 8.944 meters per second. But note that this is 120 joules, and this is 30. So the total energy at C is still 150 joules, right? How much work is done by friction? So the work of friction is mu mg times D. And this is 0.25, so 0.25, 3, I'm going to say 10, and this was 3 meters. The distance from C to D in the region of friction was 3 meters. So this is 9 times 10 is 90 times a fourth. So what's a fourth of 90? 22.5 joules. So the work done by friction will be 22.5 joules. And what that's going to mean is, again, EC minus the work of friction is equal to ED. But at ED, remember, and I'm going to go to a new slide, remember at ED, we have mvd squared over 2 plus mgyd. And that is equal to the energy at C minus the work of friction. And if you plug this in as mu mgd, we got 22.5 joules. So this was 22.5 joules. You could again write the energy at C as this, or the energy is equal to MVA squared over 2. But we know it's 150 joules, so we're just going to write 150 joules here. And so we know what this has to equal. What was Y at D? Well, Y at D was still 1 meter, right? C and D were both 1 meter high. So we know that this is 3 times 10 times 1, and this is 30 joules. And that just leaves us with 3/2 times VD squared. To find VD, move that over, right? I get 52, so what is 150 minus 52.5? I get 97.5 joules. So 3/2 VD squared is 97.5 joules. And if I multiply that by 2, divide it by 3, I get that VD is square root of 65, which is 8.06 meters per second. But before I move that over, what is the energy at D? The energy at D is 97.5 joules. It's EC minus the work of friction. So 97.5 joules and 8.06 meters per second. And now, when it drops to the bottom, when it drops to E, right, Y of E we found was -1 meter. So the energy at E is mgye plus mve squared, plus, over 2. And that energy is equal to ED, which means that energy is equal to 97.5 joules, or symbolically, it's equal to this right here, right? Either way you want to do it, doesn't matter. If this is -1, this is -3 times 10 times 1. This is -30. That means that MVE squared over 2 is equal to 97.5 plus 30 joules, which is 127.5 joules. And VE is then multiply 127.5 times 2, divide by 3, take the square root, that's the square root of 85, and I get 9.22 meters per second. Okay. So I have that at E, my energy is 97.5, the same as at D. And we already said that, and this was 9.22. And this is -1 meter, and this is -1 meter. The velocity doesn't change at F from E to F because there's no friction and there's no change in gravity, no change in height. I mean, so no work by gravity. So let's look at this. What's going on here? It starts off with 150 joules of energy at A, and that's all kinetic energy heading to the right. Still has that same kinetic energy at B, 150 joules. And when it pops up to C, right? Some of the energy becomes potential energy and is stored in gravity, in gravitational potential energy, and some of it's the velocity, but the total energy is still 150. And so what we see is we see a reduction in velocity. mgy here is 30 joules. 30 joules of this 150 joules of energy that the particle has, 30 joules of that becomes potential energy of gravity. It's stored in gravity. And so it slows down as it goes up to the top of the hill. Then it cuts through a region of friction. And when it passes through this region, it loses energy to friction. And we know how much it lost. We figured that right here at the bottom, that it loses 22.5 joules of energy to friction, just mu times mg times d. The work is the force, mu mg, times the distance that it traveled through, or that force was applied. Okay, so that's how far it traveled through the friction region. So as it moved from C to D, it lost 22.5 joules, right? Whoops, I have a small error here. This isn't 97.5. This is actually, I totally messed that up. This is actually going to be, too late at night. Let's see what I did wrong. Because the energy loss should just be 22.5. So when I wrote this 97.5 for D, I forgot about the 30 joules that were here. So this should really be 127.5 joules. And then I took another 30 away, which is how I got 97. So this is really 127.5 joules. And this is 127.5 joules. Once it passes D, right? Once it goes from D to E, there's no friction from D to E, and there's no friction from E to F. So it's not going to lose any energy when it travels from D to E. And it's not going to lose any energy when it travels from E to F. The energy was lost to the total energy. We lost 22.5 joules of energy to friction in our total energy. And what that means is these are then going to be changed. VD is still the same. Where I have to fix things, this is still 8.06 meters per second. Where I have to fix things is when I found E, this should have been whatever it was, 127.5. So if this is 127.5, if I add 30 to that, that becomes 157.5 joules. Adding this 30 to the other side of the equation, multiplying that by 2, 157.5 times 2 divided by 3, square root of 105 is 10.25. So this is, let me actually do it for you correctly. So the energy at E is mgye plus mve over 2 squared is equal to 127.5 joules. Okay, we know that this is 3 times 10 times minus 1, so that's minus 30, plus mve squared over 2 is equal to 127.5. If I add 30 to both sides, I get mve squared over 2 is 157.5. Multiply by 2, divide by 3 because the mass is 3. And what I get is that VE is the square root of 105, and that is 10.25 meters per second. For F, the velocity at F is the same. So the velocity at F is the same because there's no change in height, so there's no change in potential energy of gravity, there's no springs, there's no friction. So this was, what did we say, 10.25? 10.25 meters per second and 10.25 meters per second. So sorry about that. It's really easy to mess these up. That's why I like to write tables. But yeah, simple algebra is going to kill you, especially the more math you learn. But what I wanted to show you here is that, so A and B are level, so A and B are the same. It starts with 150 joules of kinetic energy. When it goes up to C, it loses 30 joules of kinetic energy that gets stored in gravitational energy. The force of gravity actually does negative work on it as it goes up, so it loses 30 joules, but it's still stored in there. So it goes into the potential energy of gravity. And we say that the energy at C is the potential, 30, plus the kinetic, 120 joules. And then we just solve for what that is. We solve for that here. And we found that, of course, the velocity slowed down. It went up a hill. It lost kinetic energy to potential energy of gravity. However, it still has a total energy of 150 joules. It passes from C to D, and it loses energy due to friction. And that energy is lost for good. So once it goes from C to D, it loses 22.5 joules. And for the rest of its motion, it only has 127.5 joules available, period. That energy that was lost to friction is lost forever for the rest of the problem, right? So we had to handle the energy at C minus the work of friction is equal to the energy at D, and then these three are equal. So these three are equal, and these three are equal. But EC minus work of friction is equal to EB, right? So EA is equal to EB is equal to EC, and ED is equal to EF, or EE is equal to EF. And then you have this little problem where friction steals energy out of the system. Now, as it goes back down the hill, it's converting potential energy back into kinetic energy. And in fact, it travels further down. Gravity does more work on it because it actually goes below our zero level. So it speeds up greater than its initial velocity was. And that's because that change in potential energy actually was more than the friction. It actually ended up gaining energy back when it dropped lower, which is a little weird to think about. But yeah, that's just kind of odd, I guess. It's a weird way to look at it, but it all works out. And yeah, it's what it is. Okay, so we should probably double check that at EE it has mgye plus mbe squared over 2, and that's equal to energy, but because this is negative, it added some. Yeah, and that's fine. Just wanted to be sure. So, okay. As you can see, these problems are actually quite simple to do as long as you remember how to do the friction correctly. However, they get super tedious. They can get really, really tedious. This is why when we do this wrap-up roller coaster problem at the end, I'm not going to get to numbers. It just takes too long. So, in this simple example where we had these energies, so this is, let's go back to this kinetic energy, and this, it stopped, so zero kinetic energy, and there was friction. Where does the friction go? Okay. What I'm asking there is, the kinetic energy all turned into friction. But what did that friction become? And you should know this answer. You can know this answer by rubbing your hands together. What happens? It turns into heat. Um, Friction actually gets translated into other forms of energy, is what's happening. We're actually still conserving energy. It's just we're losing energy to other thermodynamic processes, and we're losing it to things like a change in the crystal structure, if you know your chemistry. The, the heat is actually causing things to break apart, or it may be causing things to do weird things in your substance. So things can be lost, but in our model, we're simply saying friction sucks energy out, and we don't care what kind of energy that becomes. Okay, so just keep that in mind. In this course, we don't care about the actual physical processes once we have the motion solved. And that kind of sucks, but hey, you gotta leave something for later courses, right? For your chemistry and your materials courses and your engineering courses. So just remember that we're only concerned with how the kinetic energy is changed into potential energy, or how much energy is lost and not available as potential or kinetic. All right, changing gears and getting away from that stuff. We're going to talk about something called power. And power is actually something you're probably familiar with. You probably use the word, and you may not understand what the word means in the physics sense. Power is actually the work done, or the time rate of change of the work done. So if we take our work, which is Newton meters, it's energy, and we divide it by how much time, we get something called the average power. And if we take the derivative, the time derivative of the work, we get the instantaneous power. What that means is, in effect, we can write the work is P dt, and basically if we multiply the power times time, we get the work. Not a huge deal. It's actually in practice super easy. This is, again, plug and chug stuff. But power, this is joules over seconds, and a joule per second is a watt. So the wattage of something like a light bulbs have watts. The wattage is a measure of how much power, and power is a measure of how much energy is used in a time interval. So how much energy you're using over time. One thing we should talk about is bulbs are usually given in kilowatt hours. You're usually charged, well, bulbs aren't. Bulbs are given in watts. But your electricity, your electric bill is kilowatt hours. It's a measure of how much power you used, how many kilowatts in each hour, right? So we have these things called watts, and watts are just joules per second. Power is a scalar. It has to be a scalar, right? We don't assume that time has a direction, and energy definitely doesn't have a direction. Therefore, power can have a direction in the sense that energy has a direction. We can talk about negative power and positive power. We never do. What I would liken it to is if you've ever used a power screwdriver and you're screwing a screw in, or you're pulling a screw out, the power is not a vector. It can be negative or positive, but that doesn't really tell you anything with power, anything useful to us as humans. We're going to do a few examples of power, and once you see them, you're going to go, oh, wow, yeah, that's totally cool. Kinesiology people that study exercise, or if you like to work out on your own, we're going to do a problem that shows the power involved using the work of gravity. It's a cool problem, and it might help you understand how exercise lets you burn energy. So before we do any of that, power is a scalar. If we look at this, if we take the work and we say the work, the time derivative of the work is the power, f dot dx, right? We can see here that what we get is we get f dx over dt, and so that's fv. And because this is a dot product, we would get a cosine, right? So this would be cos of the angle between them, or fv cos of the angle between them. If they are parallel or anti-parallel, this is positive or negative 1, right? So the power is the force times velocity. The power is also the work over time, or the power times time is the work. These, and power is force times velocity. These three equations really are what we're going to use. Know that if the force or the velocity is at an angle to the force or the velocity, you'll need to include the cosine term. But if they're parallel or anti-parallel, forget that cosine term's even there, okay? So let's do a few examples. And this one's actually fun. So power, remember, is work over time. And we say you have a mass of 80 kilograms. And for exercise, you're going to run up 30 steps. Each step is 0.13 meters high. And you're going to run at constant velocity to get to the top in 300 seconds. How much power do you use? How much energy are you burning per second is what we're asking, right? So what's the force of gravity? Well, this is mg, and you're going up. Your displacement, delta y, is going up. For each step, the work done is F dot delta y, right? And so this is going to be negative mg times 0.13. For each one, you're going to do that. If we assume this is 80 and this is 10, like we've been, and this is 0.13, right? We're doing 80 times 10 times 0.13. We're doing 104 joules of energy for every step. The power that we're using, right, is our work over our time. So this is technically, there's how many of them? 300? 300 times 104, right? Joules, sorry. Ooh. So 104 joules over 300 seconds. These cancel, and what we get is we get 104 watts. So you did 104 watts of power, or you used 104 watts of power to go up those stairs. You did 300 times 104. You did 31,200. So the work you did was 31,200 joules with a negative sign. The time that it took you to do that was 300 seconds, and the power that you used was 104 watts. This leads us to something else, right? 60-watt light bulb. Do you know what that means? That tells you, when we say 60 watts, a 60-watt light bulb will use 60 watts per hour, okay? So basically, you were running and using power, the power required would have lit a 100-watt light bulb for an hour. That's how much power you expended to get up those 300 steps in 5 minutes. You would have lit a 100-watt light bulb for an hour. That's pretty good. That's a pretty decent amount of energy that you had to pour into yourself to get up that hill. You could think of this as weightlifting too, like lifting a weight up off your chest if you're doing like bench presses, or doing some kind of I don't know, even certain types of yoga, or Stairmasters, running, jogging, you can actually figure out how much energy you're using and how much energy these exercises actually use and how much energy you burn doing them. And they're pretty good. They'll get you in the ballpark, which is pretty nice. If you're into exercise and figuring out your calories and all those things, right? I already did that one. So I'm going to skip and come back to this in a second. So a 60-watt light bulb, remember that 1 kilowatt, right, would be 1.000 watts. So 60 watts, I'm sorry, would be 1,000 watts. So 60 watts is 0.06 kilowatts. So a 60-watt light bulb uses 0.06 kilowatts per hour, right? Well, your electric bill tells you how many kilowatts per hour you use. It basically adds up and gives you the number in that. And if you look it up, you might get charged 12 cents per kilowatt hour, okay? So we know that we're using 0.06 kilowatts per hour to run a 60-watt bulb, right? So if we ran it for an hour, it would use 60 watts, right? Okay, so essentially what it's saying is after an hour, we've used 60 watts. And what I want to know is if the electric company charges you 0.12 cents, so 12 cents per kilowatt hour, right? How long would you have to leave the bulb on to use up 1 kilowatt? It uses 60 watts. So what I'm asking is how many hours does it take of this thing running to use a kilowatt? Or what I'm asking is 1,000 watts divided by 60 watts per hour is how many hours? Well, that's pretty easy. 16.7. So 16.7 hours. If you ran a 60-watt light bulb for almost 17 hours, you would use 1 kilowatt and they would charge you 12 cents. So when you look at your electric bill and you see how much power you're using, or if your mom or dad ever told you don't leave a light on, well, yeah, I guess 12 cents adds up over time, but if you left a light on most of the day, you would still only be spending 12 cents a day. So you could tell them that. You now know exactly how much power that light bulb is using. And you could figure it out, which is, I guess, a little snarky, and you probably don't want to do it. You know, if your parents are like me, they probably won't be happy with you being sarcastic about it, but it's totally true. How much work is being done by the bulb? Well, remember that a watt is, so a watt is power, and power is work over time, right? So the work being done is P times T, and we know the power is those watts, right? So a 60-watt light bulb times 16.7 hours gives us the work. And that is, you guys should already know this, 60 times 16.7 is, checking my answer, is 1,000 watts. I'm sorry, it's 1,000 joules, okay? Because your watts, I'm sorry, power is in watts, which is joules per second, times time, which is in seconds, gives you joules, right? And that's the work. And your power was 1 kilowatt, right? That's how much power you ended up using in a time of 16.7 seconds. So if we multiply 1 kilowatt times 16.75 or 16.7 seconds, I'm sorry, again, it's really late here. So I'm getting super tired. The power used would be 1 kilowatt. which is 1,000 watts. That's the power. And if we multiply this by the time, so the power times the time will give us the work. We know the power is 1,000 watts. The time is 16.7 hours. So 1,000 watts times 16.7 hours, but how many seconds are in an hour? So 3,600, 60 seconds times 60 minutes in 1 hour, right? So the amount of work that this thing does is 16.7 times 3,600 times 1,000 would be 6.012, nope, would be 60.12 times 10 to the 6 joules of energy. Okay, that's 60 million joules of energy, or 60 megajoules of energy would be used by that light bulb in the 16.7 hours. That's a lot of work. A lot of work. Not a lot of power. I mean, a kilowatt's actually not a lot of power. So you can get the feeling that a joule really isn't that much. And remember that a joule's a Newton times a meter. It's the force of 1 Newton, which is essentially the force required to accelerate a 1 kilogram mass at 1 meter per second times another meter isn't actually that much. It turns out. It's watts are a much more human observable number, right? We can kind of get a grasp on what 60 watts is. 60 megajoules is a lot, and it's not a whole lot of power, right? So just bear that in mind. This problem's a little facetious and a little dancing around with some concepts that aren't particularly clear, and I'm sorry for that. But just know that the light bulbs in your house are measured in power. They're measured in watts per hour, but they're measured in watts, and watts are power. So a 60-watt light bulb is using power, and you can turn that into work over time. And so if you multiply a 60-watt light bulb by 3,600 seconds, you could figure out how much work is done by the light bulb in an hour, right? So that would be 60 times 3,600, which would be 2.16 times 10 to the 5th joules if you left a 60-watt light bulb on for an hour. That seems like a huge number, but you already know that that's really not that big of a deal. Kind of weird, right? Anyway, the last thing I want to talk about is this one. So this goes back to our power is force times the velocity. And so in this, we have a plane, right? And this plane is flying, and it's got 2 engines on it, right? And those 2 engines are putting out thrust. They're putting out a force of 3,000 newtons, each of them. So we have 2 times that. So let's make sure we multiply this by 2. That's the force on the jet. And that's allowing it to fly at 245 meters per second. The power that this plane would be required to put out in watts would be 2F times V. We did the derivation up here. That gives us FV. We should note that the force is going backwards, the velocity is going forward. Therefore, this power would be negative. It would be the power output. And we get 2 times 3,000 times 245. And that will give us watts. That's 490 times 3,000, which is 1.47 times 10 to the 6 watts. Or 1,470 kilowatts. If we want to know how much horsepower this is, what we could do is we can turn that into horsepower by noting that there in 1 HP, there are 745.7 watts. So divide 1470000, divide it by 745.7. So to make it clear, 745.7 watts. So my 1.47 times 10 to the 6 watts divided by multiplied by 745.7 horsepower per watt gives me 1971 horsepower. Your car could have 40 horsepower. Your car could have 200 horsepower. You can look at the horsepower of your car and figure out, let's say at 30 miles per hour, which we already figured out was 30 miles per hour is about 14 meters per second. So a V, let's say your car has 40 horsepower and V is 14.3 meters per second, which is about 30 miles an hour. How much force is required for this? Well, P is equal to FV, so F is equal to P divided by V, and that would be 40 divided by 14.3 meters per second, right? The thrust on your car would be, would be 2.79 newtons, which is not that much. That's really not a lot of horsepower. So let's say your car has 400 horsepower, which would probably be more accurate. Divided by 14.3, that's about 28, and on and on and on. It's not bad, but yeah, you can figure out the horsepower on your car and how that translates into force and velocity. You can figure it out for anything that's moving. If you're given the power, you can find the force, assuming you know the velocity. But that's just plug and chug. There's an example of that in your book. It's not too hard. The next to last thing that I want to talk about is something called a potential energy diagram. And these diagrams, ignore for the moment, ignore these things. I really don't like these things being on here. But I really want you to look at this shape. I want to talk about this shape. So essentially, when we talk about a potential energy diagram, we basically begin by figuring out what is the total energy of the system. And we note that that is potential energy. Potential energy plus kinetic energy is always equal to the total energy. And so the potential energy max is when the kinetic energy is 0. And we always have to note that. So let's say we note that, and actually I want to note that with red dots. So that's our maximum potential energy. And then we get the point where potential energy is equal to 0, so our kinetic energy is max. And everywhere between there, you're going to get, starting here, you're going to get full kinetic energy. Up here, you're going to get full potential energy. And so if you want to know the energy of the total system, you just look at wherever it is. But then how you use this is you compare that to the motion of the particle. And so let's say that this potential energy diagram looks like this, right? Okay. So what this is telling you is if it starts here, it's only going to make it to this point right here. It's only going to be able to get there, and then it can't get any higher because it's run out of kinetic energy, right? And if you start it here, it can't go up, but it can go down. And if it goes down, it'll make it over and head off to the left. So anywhere further to the right than this point, and it's heading to the left forever. Now imagine instead we have another particle whose potential energy max is here, right? And potential energy is 0. And we see that and we can see that if it's put here, it's going to go here, stop, and turn back. The highest point is the point where all the kinetic energy becomes all the potential. And so we make these potential energy diagrams to look at basically what we say perturbing a object, so, or a particle. So let's forget this for a minute. And I want to perturb this thing. I want to imagine that I have a particle that I put right here. And it has this potential energy maxed, right? So this is the maximum energy. Let's say this is 100 joules is the maximum potential energy. That means that the energy is always 100 joules. And at the bottom here, it'll have kinetic energy of 100 joules. And everywhere else between it'll have something. But let's say I start this and I perturb it by pushing it. Well, before I do that, I want to push it to the left. If I push it to the left, it'll get up to the top here and head off to the left forever, right? Because it has enough kinetic energy, well, enough energy to convert kinetic energy until it gets to the top, and then there, it might stop right here, or it might go forever if it has a little bit of kinetic energy left. However, if it goes to the left, it will go down, come back up, it runs out of kinetic energy, turns back, goes over this, and heads off to the right, just like in the other case. That's what we're looking at with the motion. We use potential energy diagrams to kind of see how things can move and if things are trapped in potentials. This is fairly common for studying like electrons that are attached to an atom, right? That this is where all their kinetic energy becomes potential and they just go back and forth. And if you can give it a little bit more energy, it can eventually get over this hill and head off to the right, right? So as long as it has more energy than this potential energy here, it can get over that hill and head up and then maybe head back. Potential energy diagrams are pretty easy to read. They're a visual tool to understand where a particle will be trapped in a kind of a restoring force, meaning that you could imagine this as like a particle on a spring here where it's going back and forth. Spring is stretched, spring is compressed, spring is, blah, 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 blah. You can do that. The main thing to remember is that when you look at these, the highest peak is where the potential energy is the maximum. The bottom peak, or the bottom limit, is where the kinetic energy is the maximum. Somewhere in here, and I don't know why I can't draw a straight line, but yeah, let me not do that. So somewhere in here, there's a point where half kinetic energy plus half potential energy is equal to the energy. So where they're equal, somewhere in between there, the kinetic and the potential energies are equal. In general, just look at a few of them, look at that part of the chapter, make sure you're familiar with them. I think we're gonna have one homework problem with them, but you really just need to be familiar with what they tell you and how to use them. But all they're really for is to see where things get trapped in what are called potential wells. And these are potential wells where they don't have enough energy to get to the right or left. They just go back and forth. And if they do have enough energy to convert the kinetic energy here so that they still have some kinetic energy left when they get to B, then they head off to the right, or they can go to the left or whatever. It's not too hard to understand, but just keep in mind that they're going to show up somewhere in your science career, and you better learn them at some point. And since we're talking about potential and kinetic energy, we might as well talk about them for a second right now. All right, so putting everything together, the roller coaster problem. I'm going to make one small change here, and I'm going to say from here to here, this distance d has friction. Okay, there's friction here. But that's the only spot here that we're going to have friction. And I'm going to make one other change. This thing is initially on a compressed spring that's compressed some delta x, just so that we have some spring in here, right? Oh, I just realized why the heck, I'm like, why is that being so hard to, so here, this is friction, and it's some distance d, and we're going to say that initially this thing is compressed delta x. This is on a spring with a spring constant k, delta x, and we're given the mass is, I don't know, 600 kilograms. And this delta x is 0.9 meters or something. I don't really care what it is for now. The only region with friction is here, and this is going to be some delta x, which is d, which is whatever you want to call it. I don't care. I'm not going to put numbers in, so I'm not going to talk too much about this, but we're going to assume a couple things first, and that is that at any point, the normal force, at any point that we care about, the normal force is mg. Second of all, let's look at places where we might be interested in the motion. So at the beginning, when delta x is 0.9, we're going to care about that. And it hasn't started moving yet. And then it's released and it's going to shoot down. So once it clears the spring, so at B, when delta x is 0, at B, this I should say is negative, right? So at A, when delta x is negative 0.9, it's compressed the spring. B, as it passes the equilibrium point, and it's going to have some velocity, it's also going to have some potential energy here. And we will talk about that for a second. Then we'll want to know, right before it hits the friction, we'll care about C, because it's going to gain kinetic energy as it drops. The potential energy is going to turn into kinetic energy. After the friction region, we're going to want to know what the velocity is. At the top of this hill, we're going to want to know what the velocity is. Maybe, again, at the bottom of this loop, and then at the top of this loop, sorry, I should call that G, right? At the top of this loop, and maybe as it leaves. I don't care. So we have, before it leaves, when the spring is compressed, after it leaves, when it gets to the bottom, after the friction, when it gets to the top of this hill, when it gets back to the bottom, when it gets to the top of the loop, and when it gets back to H. And we know that this will be R plus R, right? It'll be 2R, because whatever the radius of the loop is, that'll be the height at G, okay? So the first thing that we do in our algorithm, we've already done. And that was, we chose positions. We actually chose A, B, C, D, E, F, G, and H. The next most important step is, where is y equal to 0? So, to be honest with you, I want to be able to calculate this friction in the easiest way possible. So I'm going to call this my y is equal to 0. And I already know the height, right, to A and B. And I know that this is given to me. It says R hump. So this is, so R1, and this is, or R hill, and this is R loop, right? And they'll be different. But whatever, I'll know the height here, and I'll know the height is 2 times the loop here. So I've chosen my y is equal to 0. And I'm going to write y, and I'm going to write v. I'm going to write x, at least for a couple of these. And then I'm going to make notes of energy. The energy, right, that I can get rid of. So y for A and B here is 38.3. And it's positive 38.3. Right? They're both positive up at the top. X here was negative 0.9. This is how much we've compressed the spring. This is 0. It's cleared the spring's equilibrium point, and the roller coaster is heading to the right. It's initially at rest. So rest. So VA is 0. I don't know what VB is. VB is going to be something. The energy this has is mgya plus mva squared over 2 plus kxa squared over 2. At A, the spring's compressed. It has energy from potential energy of gravity. What it doesn't have is this. And then at B, it has mgyb plus mvb squared over 2, but there's no spring. And now I want you to look at something that I didn't really talk about before, but we know that the total energy at A is equal to the energy at B, assuming no conservation, right? Or no non-conservative forces. The energy at A is mgya plus kxa squared over 2. And the energy at B is mgyb plus mvb squared over 2. Since these things are equal, right, you can set these two things equal to each other to solve for VB, let's say, because we already know XA and we know K, assuming, and we know M. But YA and YB are equal. So these two terms will actually cancel when you set EA equal to EB. What I want to make sure you know, though, is the energy at A is this. And the energy at B is this. But when I set EA equal to EB, these cancel, and you get KXA squared over 2 is equal to MVB squared over 2 plus MGYB plus MGYA. But YA and YB are equal, so these things cancel, and you only have to solve that. In fact, the 2 cancel, and you get VB is the square root of K over M times XA squared, all square rooted, right? So you can solve that pretty easily. When we drop, the only thing you need to remember is that Y is now 0. We've decided that Y was 0 at C. This doesn't matter anymore because there's no more springs. So we don't need to worry about X except for A. We can dump all those. VC is going to be greater than VB, but the energy at A is equal to the energy at B is equal to the energy at C. And the energy at C will simply be MBC squared over 2. Because there's no spring and YC is 0. And this is equal to EA, which is equal to EB. And you could solve for VC using either of these. But you can't cancel the YA, YB terms. That's what I'm getting at. So EC, which is equal to MBC squared over 2, is equal to MGYA plus KXA squared over 2. Or it's equal to the MVB, or you could find this as a number and just plug it in and get it. That's all well and good. Now remember that once we get to ED, right, this is not equal to ED. Not true. ED is equal to EC minus the work of friction from C to D, as we did in the earlier problem. And then ED, right? ED will be MVD squared over 2. This will be ED. That's what ED will equal. So whatever EC equals as a number, you could plug in here and find the work of friction as mu mg d, not d, little d, right? So this is mvc squared over 2 minus that is what ED is equal to. After that, EE is equal to E, ED is equal to EE is equal to EF is equal to EG is equal to EH. And here, what happens is it has MVE squared over 2 plus MGYE. Here, YF is back to 0 at the top. So I get rid of this stuff so that I can actually see my Y's. D was 0. E was whatever R the hill was. F was 0. G was 2 times R of the loop. If we're given R of the loop, double that will give us the height to the top of the loop. We don't really want to deal with it anywhere but the top of the loop or the top of the hill. Why? Because our N will not be simply mg. So yeah, if we wanted to know, we could figure out what angle this is at and what N is at and all that. Don't do that. Oh, no, that's only assuming there's friction though. The velocity in the direction perpendicular to the track, so if the track's running like this, the velocity going that way, you could find at any point, and the only thing you need to figure out is what Y is. We wouldn't need this N. The N along the friction track is mg. I was being crazy. Like I said, it's late. So G is 2 times R of loop, and H is 0 again. So I figured out all my Y's. My V's I'm going to have to find using energy. But again, EA is equal to EB is equal to EC, and ED is equal to EE, on to EG, right, or EH. All of them from D, E, F, G, and H are equal. And then EC minus the work of friction from C to D is equal to ED, or ED is ED plus the work of friction is equal to EC, whichever way you want to do it. The point being here that the energy is going to change just like before. It's going to lose some of its total energy going from C to D because of the friction. It's going to take energy out of the problem. So when you do these roller coaster problems, in general, you start at one point and you can start, in general, you'll know maybe the energy at A is a number. You'll be able to figure it out, and it's like 700 joules. And then you'll find the velocity at B and the velocity at C, because you'll have to use potential energy. And then you can find the work of friction, and you can find the total energy at D and the velocity at D. And once you have that, whatever this, the energy at D, let's say, is now 330 joules. The energy at D, at E, at F, at G, and at H is all 330. But that's equal to the potential energy plus the kinetic energy. And you can do what we're doing. And all you do is all this over and over and over again. You do this over and over and over again, with the warning that you can't set like EB equal to EE, because there was friction that happens when it passed from C to D. It lost energy going from C to D. So you know that there's a frictional loss in there somewhere. What you could do is you could put EB minus the work of friction is ED, because EB and EC are equal, right? You could use EA minus the work of friction, EB minus the work of friction, or EC minus the work of friction. It doesn't matter. They'll all give you the value of the energy at D, which is another thing that makes this really nice. If I asked you if I gave you all this and then I said, well, what is the energy or the velocity at h, right? And that's all I asked you. I didn't ask you for any of this, right? The energy at h is mvh squared over 2, right? And that, let's say this, there is no friction. Imagine there was no friction. So the energy at A was kxa squared over 2 plus mgya. That would be equal to EH by conservation of energy if there was no friction. No friction. And all I would have to do is compute this, and I wouldn't have to care about any of this. Because again, the path doesn't matter, right? The only time that the path matters is when there's a non-conservative force involved, such as friction, which is why we have to figure out how much energy is lost to friction and then kind of start the problem over with that new value. So just be careful with that. Know that you don't have to pick them in order. You don't have to solve EA, EB, EC, ED, EE. If it makes sense to you, solve EA and then EC, and then solve for D and then go D to G. Whatever you need to do, you can do. But the algorithm is write down positions, A, B, C, D, E, wherever you think you need them. Write down the energy at those positions. Write down the variables at those positions. And then if you have friction, figure out which energies are equal and which are not. Okay, and there's a couple subtleties that you'll pick up on just doing these problems in general. But on an exam, what I'm going to want to see is I'm going to want to see that you draw it, you pick your positions, you give me the energies there, the types of energy, and you give me the variables there. And then you can put them into equations that make sense. And if there's friction in it, you can handle the friction. You can deal with the friction, right? So you really just need to do these. They're not too hard. So where do we go from here? Where are we going to go tomorrow? Well, tomorrow, we're actually going to talk about Newton's laws in a whole new light. And that new light is the fact that we've already seen that A is dv dt, right? So imagine what would happen if you took a force times dt. What does this give you? Well, this is mdv dt times dt, right? And what you would get is you get mdv. Well, that would give us m, if this was v initial and this was v final, this would give us m v final minus mv initial. This is something called an impulse, and the impulse is force dotted with time. But force dotted with time is equal to change in something called momentum. And momentum is simply the mass times the velocity. And it turns out that Newton's laws, if you write them as time derivatives of the momentum, because mv times d dt is actually a force, right? I hope you can see that. There's a dv dt. If m is constant, you get a force. Or m could be changing with time. M doesn't necessarily have to be constant. So what we're going to do is we're going to talk about how impulses work. If we apply a force for a certain duration of time, we get a change in momentum. Linear momentum is what that's called. We're going to use that and the fact that that's conserved as long as there are no forces. If F were 0, then the final is equal to the initial, right? But when we have a system of particles, so we have more than one mass attached like on a string, if the momentum of one changes in the system, the momentum of the other has to change as well so that the momentum's always 0. And that leads to things called elastic collisions, where the momentum doesn't change for the whole system after something happens, after a collision happens, or inelastic, where things stick together, the momentum still doesn't change, it's still conserved, but the energy is not, and we'll talk about that. You probably learned those if you've taken physics before. You probably learned about elastic and inelastic collisions. We'll talk about those. And then we're going to become rocket scientists. I'm going to show you how to do something called the rocket equation and what it means and how you would compute the amount of thrust necessary to get a rocket shooting around the solar system. And that's actually pretty cool. Rocket equation is used for rockets, but it's really variable mass. It's if the mass weren't constant. And you might think about this, and I'll tell you the answer tomorrow. What would be a system that doesn't have constant mass? And the hint here is don't think of solid objects, think of collections of objects. Okay, anyway, hope you're all safe and happy and healthy, and I'll talk to you soon. Bye.